Hi, welcome back to Math 111. I'm Anne-Marie Harden. I'm your instructor in this class. We are going to take a look at the graphs of functions. Now, this is the next section in Chapter 1. So this is Section 1.6. And some things to keep in mind here. The fundamental idea of graphing a function is that we are drawing a picture of the set of points that satisfy the function. So what we're saying here is if we're going to graph this function, let's just do this on Desmos. F of x equals x squared minus x minus 6. So on Desmos, I can just type f of x equals x squared, get out of there, minus x minus 6. What I have just done is ask the computer, and I asked the computer to do it because it's quicker than I am, to draw me a picture of all of the XY pairs for which this statement is true. In other words, for every point on this curve, Y, if I click on a point like that one right there, yes. If x is -2, and if I plug -2 into my equation for my function, x squared minus x equals 6, I will get out y equals 0. This is what it means to graph a function. We are drawing pictures of all of the points for which that equation is true. Here's another one that I can read easily. Maybe. If x is -4, y is 14. Now notice that there are lots of points in between these ones that we can read easily. But they're hard to read. If y is -3, x is 6. But at every point on this curve, this equation is true. For every point on this red line, for any x, the y half of that point is given by this equation. Our graph is drawing pictures of the set of points that satisfy that equation. When we do this by hand, we tend to make tables and then draw smooth lines through those tables, through the points on those tables. Kind of laborious, but that's what we do when we do it by hand. And what I want you to understand is that's what the computer is doing too, okay? When the computer graphs these things, whether we're doing it in Excel or on a graphing calculator, it's just drawing lines through points, okay? No magic. It's just faster than we are. Okay, we can also talk about piecewise defined functions, and we've worked with these, I think. Maybe not. I don't remember. It's been a busy week. But, so piecewise defined function. What the piecewise defined function does is, remember we've talked about domains? What this does is this breaks our domain into pieces, hence the name piecewise. So what we're saying is that for every x less than 1, my function is going to be defined by 4 minus x squared. Yeah, we did the rocket example. This is just like that rocket example where the rocket went up and came back down in the first 20 seconds, and then it was on the ground after that. So if x is less than 1, then my function follows this parabola. If x is greater than or equal to 1, then my set of points follows the line y equals x minus 3. Okay, so what that means is that If we get closer and closer and closer to 1, my y value is, as x gets closer and closer and closer to 1, my y gets closer and closer to 3. But not ever actually equal to 3 along this parabola, because the minute x equals 1, we go to my second line on my graph, and my y value jumps to 1 minus 3 is -2. So this open circle means 3 is not on this part of the graph, but on this one. And one of these 2 points for x equals 1 has to be open. Otherwise, we don't have a function because we would fail the vertical line test, right? All right. I hope that explains piecewise functions. Ask me whatever questions are bothering you about this. Forums are a great place to talk about this sort of stuff, as is class time. But in between class time, post on the forums. Okay. Now, I want to talk about some special points, and they're highlighted on this graph. This guy and this guy are special points. What's special about them is these are the points where the function crosses the x-axis. Remember that for every point in the x-axis, the y-coordinate of that point is 0. So these are called the x-intercepts, or sometimes we call them the zeros of the function. This guy up here is also a special point. He is called the y-intercept because it's the point where the graph crosses the y-axis. All right. So the zeros of a function are the places where y equals 0. Or, another way of saying that is the spots where the graph of the function crosses the x-axis. Okay, I want to talk about symmetry, because symmetry is actually very important for functions. Remember symmetry for points? We defined points as being symmetrical about the y-axis if what? Symmetrical about the y-axis. That meant the y-axis went right in between them and they were mirrored, right? Their y's had to be equal and their x's equal in magnitude but opposite in sign. So the way that translates into functions is if we can plug in the negative value, if we can replace negative x for x, in other words, if we can take out all of our x's, simplify it to negative x, plug in negative x, and then simplify our function and get back to what we start with, then that function is symmetrical about the y-axis. Let's look at an example here. Okay, the function y equals x squared minus 6. If x is, not that one, 2, y is negative 2. If x is negative 2, y is negative 2. So what I'm trying to show you here, and my graph is not behaving itself, okay? Negative 2, 2. It's on my graph, right? Over here to the other side. And 2, negative 2. So my y's are equal and my x's are equal and opposite. The other way I can check that is if I put in negative x in the place of my x and then simplify, I will get back to exactly the same thing. This graph is symmetrical about the y-axis. Okay? There are other examples. Let's see. This is another example of a symmetrical, or a function that is symmetrical about the y-axis. If I replace all of my x's with negative x and simplify, I'll get back to the same function. Okay? These types of functions are symmetrical about the y-axis. Now, we aren't going to talk about functions that are symmetrical about the x-axis because those wouldn't be functions, would they? Think about that for a minute. But we are going to talk about functions that are symmetrical about the origin. And let me show you an example of that. This is an example, whoops, not quite, of a function that is symmetrical about the origin. Now, the reason I know this is because let's take a look at a point like fine. No, okay. The point so let's see what f of negative 2 is. F of negative 2 is negative 8. F of 2 is 8. So what I've done is I've replaced all of my x's with negative x's, and I got the negative of my function. Does that make sense? It's not good enough to just check it for one number. You actually have to do the arithmetic. So let's see what happens if I do this. Y equals negative x to the 5th minus 3 times negative x to the 3rd. Yeah, this will work. Okay. So do you see what I did? Compare my two functions here. This one is my original. The red line represents my original. The purple line represents that same thing with all of the x's replaced with negative x's. Do you see the relationship? One of them is the other one turned upside down. What that means is replacing, if I put in negative x, I get out the opposite of y. Okay, so that's what this statement means. It means that f of negative x equals negative f of x. This function is symmetrical about the origin. Okay, now I want you to notice something. This thing that I said was symmetrical about the origin, what is the degree of all of the exponents? Odd, right? Yeah, that's not a coincidence. We call these functions that are symmetrical about the origin odd functions. If they're symmetrical about the y-axis, like the one I started with here, this one, let me prove this to you. So if I replace all of my x's with negative x, what do I get? I get the same thing, right? That's the whole point, yes? Yes, yes it is. Notice the degree of all of the variable terms. What are all of my exponents? They're all even, right? Not a coincidence. we call these functions that are symmetrical about the y-axis even functions. So if you can take your graph and fold it in half on the y-axis and get a mirror image, so your two lines lie right on top of the other, you have an even function. Okay? All right. It's more complicated to do that with it being symmetrical about the origins. We're not going to use that imagery. Okay. So let's determine if these functions are even, odd, or neither even nor odd. And we're not going to graph them first. We're going to do this algebraically. So let me get a blank slide. Get down to where we're at. There we go. And we are going to start by working on f of x equals 5 over 2 minus x squared. I'm using my finger. I'm going to have to get my stylus. Let's see. F of x equals 5. I don't think this stylus will work, but I'll try it. 5 over 2 minus x squared. Okay. What do we have to do to see if it's even? So first that question, is it even? The answer is we look at f of negative x. And let's see, the way we do that is we replace all of our x's with negative, sorry. All right, guys, let me go get my better stylus. I'll be right back. It's just right over there. Give me a sec. Okay, better stylus. 2 minus, whoops, gotta make that a pen, not an eraser, minus negative x squared. Now if we simplify, we end up with 5 minus 2, or 5 over 2 minus negative x squared is just x squared. Well, this is the same as what we started with. So this function is even. Okay? Yes? No? Yes. Okay. Let's try another one. Let's try g of x equals 5x over 2 minus x squared. It's almost the same thing. G of x equals 5x over 2 minus x squared. To check this, we replace our x's with negative x's. All of them. And simplify. And what we end up with is negative 5x all over 2 minus x squared. That's almost the same thing as what we started with, right? What's the only difference? This negative 1, yes? So what we have is actually negative 1 times what we started with. The shorthand way of writing that is negative g of x. So this function is odd. Do you see the difference? Okay. I want you to check these others and see what you come up with. And let's take a look at what the results are. Okay, if we plot the first one, we get this. We get this. So you can do this on your TI. In fact, these are screenshots from a TI. Plot 5 over 2 minus x squared. Be sure your denominator is in parentheses. You're going to get this graph. If you look carefully, you can see that this graph is symmetrical about the y-axis, meaning if I fold it in half on this line right here, the two parts of the graph would lay right on top of one another. So this is an even function. Remember that my algebraic manipulation proved it to me that that was an even function. So this next one, 5x over 2 minus x squared, is an odd function. And sure enough, if I graph this, and what I'm looking for is, if I draw an imaginary line through the origin going from upper left to lower right, I can see that my graph is symmetrical, sort of, about that line. Actually, what it says is if I folded this in half on both axes, so first folded it in half this way and then folded it in half that way, everything would collapse down to a single line. So this guy is symmetrical about the origin. Yeah? Okay. This one is odd. Now functions don't have to be either even or odd. They can be neither. Like this one. Okay? If we do the algebraic check on that one, let's do this. Let me erase my work here. Almost got it. All right, work is all erased. Okay, so let's check that third one. The third one is h of x equals 5x over 2 minus x to the third power. So h of x equals 5x over 2 minus x to the third power. Yes. Okay, now I'm checking to see, is this function even or odd or neither? Neither is as valid an answer as anything else. So h of negative x. So we replace all of my x's with negative x's. And you're probably thinking to yourself, what's going to be odd because all of my exponents are odd. Let's look. 5 times negative x is negative 5x. Okay, so far so good. 2 minus, now, negative x to the third power is negative x to the third. And this comes out to be negative 5x over 2 plus x to the third power. So what this does, so this isn't exactly what we started with. It's also not negative 1 times what we started with. This function is neither even nor odd. And that's what our graph shows us. So this little lump right there, that ruins our symmetry. And it makes the function neither even nor odd. So this guy's even, this guy's odd, and this one is neither. All right, I want you to do on your own this one and this one. So pause the video here. Make sure you know how to do this. And what you should get is that number 4 is even. And number 5 is also. Let's check number 5. I'm not sure it's actually even. Let's check that. That is, let's see, x squared minus x over 100 minus 1. Okay, so this one's even. This one looks like it might be even, but we're going to check it real quick. So j of negative x equals negative x, whoops. That's not the right way to write that, and it makes a big difference. Negative x squared minus negative x over 100 minus 1, which is equal to x squared plus x over 100 minus 1. This guy is neither even nor odd, so he's a neither. But this is a good example of when your graph is misleading, because the graph looks like it might be even, but when you check it algebraically, it's not. So you actually have to do the check. All right. We're almost done. I know this video is getting a little long. Hang in there with me. I want to talk about function behavior. And what I want to talk about is increasing versus decreasing versus constant. So this is pretty intuitive, guys. This function, if we always read functions from left to right, the same way that we read our English. If a function tends to increase, so if its y's tend to get bigger as we move from left to right on the x-axis, then it's increasing over that interval. So this function is increasing on the interval, and we always write it on the x's. So from -4 to -2, my function's increasing. Or in interval notation, we would write that as -4 up to -2. Where else is my function increasing? Well, it's increasing here, right? From 3 to 5. And here, from 5 to 6. So I want you to notice I'm always talking about on the x-axis, okay? So what we're talking about is regions of the domain, yes? Okay, that's every place that it's increasing. I'm going to erase this scribble here. What do you suppose decreasing means? It means exactly what you think it means. It means going downwards. So we're going down here from x is bigger than -2 until x equals 3. That's the only place we're increasing, right? But we got a little spot right here where we're constant. And we're constant between x is 4 and x is 5. So increasing, decreasing, and constant are very intuitive. They mean exactly what you think they mean. We tend to describe them as intervals on the x-axis. Okay? And we just look at that and we get it from the graph at this point. In future classes, specifically in calculus, we'll talk about how you do that, not from the graph. But for now, we're only going to do it from the graph, okay? So we've got special names for some of these points. Let's see, I think this guy. So this point here that's at the top of the hump, it's the biggest point in the region, right? It's called a local. You can't probably read that. It's called a local maximum. Okay? This guy down here, where he's the smallest, is called a local minimum. And generally we pick up, so we can define minimums and maximums on our same regions. So this guy here would also be a local minimum. Yes? This guy would be a local maximum. So what we're doing is we're looking for the biggest, the highest point, the biggest y between a certain set of x's. Okay. This slide just says exactly what I said in words instead of in a graph. What I want you to be able to do is understand this, but understand how these words relate to that picture. So I'm going to leave this for you to puzzle over. And if you have any questions, be sure and ask me, okay? All right, I already talked about maximums and minimums. Again, this slide is the word version of what I said here with the green points. Be sure you can relate these words to that picture. I'm not going to read them to you because I really don't want you to fall asleep, but I want you to read them to yourself. And if something doesn't make sense or if you can't parse it out for yourself, then please ask me the question in class, because if you're having troubles, there's a good chance somebody else is too. Put it on the forums. Maybe with conversation you can hash it out with your compatriots. But let's talk through anything that's confusing you here, okay? All right, so we're going to work some examples here. And this is going to get a little long. It's a little tedious because we're going to do a lot of stuff. But this is our graph. So we are going to work on this graph right here. And I happen to know what this is, but it doesn't matter because all we care about is the picture. Okay? Let's see what we're going to do with this picture. We are going to answer all of the following questions. So we're going to start with the domain. What is the domain? Oops. The domain, remember, is the region of the x-axis that's included by the function. In this case, the domain goes from -4 all the way up to 4. And these closed circles here and here mean that -4 and 4 are both included in the domain. So my domain is going to look like, and we're going to write this domain in interval notation. I'm going to insert it right in here. I'm going to write the domain equals, in interval notation, we want to bracket because -4 is included. -4 is my smallest x, so we'll start there. We go up to my biggest x, which is 4, and it's included in the set, so we put another bracket. So that is my domain. My domain is the set of all x's between -4 and 4. Okay? All right, let's erase this chicken scratch. Because the next question says, what's the range? And the range, remember, has to do with the y's. And our range is just the set of all y's from the smallest y to the biggest y. So what's the smallest y you see included on my line, on my graph? And -3, right? What's my biggest y? 3. So my range is going to be the interval, and again, both endpoints are included, from -3 to 3. Notice that my biggest y does not go with my biggest x. That's okay. Remember I said that range the domain and range are in no way ordered. They just give us the endpoints. Okay? So the domain is a set of all x's. The range is a set of all y's. All right, f of 2. I don't have an equation for the function, so how do I do that? I look at my graph. Okay? F of 2 means what is y when x equals 2? Which is that point right here. If x is 2, y is 0. So that means f of 2 equals 0. Okay? So now, let's talk about x-intercepts. X-intercepts, remember, are where the graph crosses the x-axis. We've got an x-intercept right here at the point -2, 0, and an x-intercept right here at the point 2, 0. X-intercepts are points, so we're going to list them as ordered pairs, so -2, 0, and 2, 0. Okay? All right. Y-intercept. The next question was list the y-intercepts. Y-intercept, remember, is where our graph crosses the y-axis, which is right here at the point 0, 3. Again, y-intercepts are points, so we're going to list them as an ordered pair, 0, 3. All right, the zeros of our function are the x-coordinates of the x-intercepts. So the zeros occur for at x equal -2 and 2. Or on paper, we can write that as positive and -2. Just stack the positive and minus sign. But XYZ doesn't have a stack plus minus, so we're going to list them out. Okay. Okay so far? All right. Now, the next question says, solve the inequality f of x is less than 0. What that means is find all the x's for which y is less than 0. So let's look at our graph. Where's our function below? Where's our graph below the x-axis? Well, here between x equals -4 and -2, right? And here between x is 2 and x is 4. So the way we write that is in interval notation, -4 up to, whoops, I get to include -4, so we'll make it a bracket, up to -2, but we have to be careful because this is strictly less than in our inequality, so we can't include -2 because at -2, my function is equal to 0, which isn't less than 0. And now, whoops, we're going to union that with the other half, which is x's greater than 2, and less than or equal to 4. Okay? Make sure this makes sense to you. This is the same thing as saying x, negative 4 less than or equal to x, which is less than negative 2, or 2 less than x, less than or equal to 4. All right. Think about that one. It might be confusing to you. If it is, be sure and ask me the questions when we get together again, okay? How are we doing? I know you guys can't answer me right now. Jot down any questions that you have, and we will talk about them either on the forums or in class. I'm just moving my answers over. Okay. Number 8 says, determine the number of solutions to the equation f of x equals 1. Notice it doesn't say solve this. It just says how many places, how many solutions are there? Well, let's think about what that means. F of x equals 1. That means we're looking for points where the y coordinate would be 1. So there would be 1 right here and 1 right here. Yeah? Yeah. So there are 2 of them. I'm just going to write this. Whoops. I'm not. I'm going to just write it here. There are 2 points. Okay. So the next question is, on what intervals is the function increasing? Now let's erase my chicken scratch and think about this. We're reading our function from left to right, and we're looking for places where the function tends to be going upwards from left to right. Well, that's all of this from negative x equals, or we do this on axis, from negative 4 up to 0. And we'll always do these with open intervals, not closed. So my function is increasing between negative 4 and 0 on the x-axis. So that's negative 4 to 0. Okay? Ignore that bullet. I don't know why it's there. We're going to ignore it. Pretend that bullet's not there. Okay. Almost done. We want to, oh, maybe that's a dot. A dot. Let's see if I can erase it. There it is. There we go. Where is f decreasing? Well, just the same thing, but on the other side, right? From 0 up to 4. So f is decreasing on the equation on the interval 0 to 4. Right? Yes. Okay. Local maximums. There's a local maximum right here at the point 0,3. So the point 0,3, and again, we're going to list this as a point because the maximum occurs at a point is a maximum. The minimums are down here, here, and here. Actually, you know what? We're going to make life a little simpler. We're just going to list our maximums as y equals 3. If your homework asks for a point, be sure and give it a point in ordered pair, okay? I think it's going to want an ordered pair. We're going to go with ordered pairs. And our minimums occur at what? -4, -3, and 4, -3. Okay? Now, when it says the maximum, it means the biggest of the local maxima. It means that if you think about the whole total domain of the function, we're talking about the highest point in all the functional universe for this function. This function has a single maximum point. It is the same as the local maximum, which is 0, 3. Now, the function does not, however, have a minimum. You might say, wait a minute, it's got two minimums. It's got two local minimums. It doesn't have a single overarching low point. It's got no single one universal low point. So this function does not have a minimum. Okay? Now, let's look at our function. Is it even, odd, or neither? It's even, yes. I hope you can see why. If not, be sure and ask me the question. Okay. So, make sure you know how I got all of these answers. You'll do some more problems like this. There will be a problem, most likely exactly like this, where I ask you to do all of these things on the test. Okay? Make sure you know how to do these things. Be sure and ask me any questions that are bothering you. Anything you don't know how to do. Okay. I am going to leave this example for you to work because this video is more than long enough, and I don't want to keep you any longer. So take out your graphing calculator or use Desmos to graph this function and find the intervals on which the function is increasing and decreasing, and write down all the local extrema. You should get a graph that looks like this. And if you're on Desmos, you can just click on the points to get the coordinates. If you're on a graphing calculator, you can use the trace function. All right. And here is another one for you. Find all of the graphs on the points which are closest to the origin. That means where y equals 0. So you're looking for places where y equals 0. And you may have to round your answers. Okay. That's it for this presentation. And when you look at this graph, by the way, it might not actually get very close to the origin. Yeah? You might find that closest to the origin is not very close at all. So I'm going to leave this to you, and we will talk about this in class when we get together. All right, everybody have a great day, and I will see you all soon. Do a little math every day.